Is it show? Okay. All right, sorry about that. Okay, thanks. So the other materials are cadmium telluride and SIGs, which is a type of chalcogenide glass. It's a type of glass amorphous material. Cadmium telluride is very popular. There's a company called First Solar, which makes it. They have big utility scale plants and so on. In fact, a lot of the work in Mike Scarpula's lab, for instance, deals with these kinds of materials, cadmium telluride, SIGs, and so on. And again, the advantage is that you can be very flexible. Somewhat lower in efficiency, but cheap and flexible. That's the idea. You can have organic photovoltaics, which we'll talk about today a little bit more. Organics has, unfortunately, suffers from very low efficiency. So in my opinion, they're not super popular, but they're very cheap because you can solution process it. They can be biocompatible and all kind of interesting things like that. And the most recent addition to this group are these Perovskites, which I won't talk much about because I'm not a material scientist, but there's a lot of excitement about these Perovskites because they seem to have efficiencies that are similar to gallium arsenide or even pretty significant efficiencies, but they can be very cheap because they can be solution processed. So this turned to be very, very popular nowadays, at least in research. What I want to talk today about a little bit is these third generation technologies, multi-junction technologies, because this is the only way that we know of where we can push the efficiencies much higher than what is possible with the other approaches. Now, why is that important? It's important because, of course, if you have a fixed area that you want to put your solar panels on, imagine your roof or, more interestingly, the surface of your car. And you're limited by what you can fit there. So the only thing you can increase is the efficiency. The higher the efficiency, more power you can get out of it, right? So that's the only technology we know. So I want to talk a little bit about it. And we'll talk more about this later. But so how do multi-junction cells work? They work because instead of having a single material, you stack up like a sandwich multiple materials. And the idea is that different materials absorb different parts of the solar spectrum more efficiently than with a single material. And this is what's schematically demonstrated here. So first of all, on the left-hand side, we have the solar spectrum. So that's the AM 1.5. You're all very familiar with this now. But this is now plotted against photon energy, not wavelength. So wavelength is decreasing from left to right. Energy is increasing. So that's blue, that's green, yellow, red, and so on. So it looks a little weird from what you're used to, but it's the same thing. This is the number of photons per unit area per unit nanometer or per EV, per energy bin. So the idea is that the top cell, which sees all the light coming in, the light's coming in from the top, will absorb the blue photons, so the highest energy photons. Okay, that means it has a very high band gap. It will absorb the highest energy photons. So that's this part colored in blue, okay, very high energies. All the other stuff passes straight through, right? The photons do not have enough energy to be absorbed, which means that they will pass through. Not exactly, some of it's lost by reflection, as we know when we talked about anti-reflection coatings, but quite a vast majority of it goes straight through. It's like glass. Glass is transparent, visible light. It behaves in the same way. Then you have another material here, which has a slightly lower band gap. So that'll absorb this green part of the spectrum, which has still high energy, but not as high as these blue. So it gets absorbed here, and then so on and so forth. So then the yellow gets absorbed next, which is a slightly lower in energy, and then red, and so on. Red is the lowest energy. So from the top to bottom, we have decreasing band gaps. So large band gap, lower band gap, lower gap. So that's how you can get very high efficiency, because now you can take these portions of the solar spectrum and absorb them in a very, very efficient manner. So it's a very clever, very, very cool idea. And this is how world record efficiencies are achieved. In fact, you can run theoretical calculations. These are theoretical numbers. What happens with one junction, theoretically, you can get something like 37%, two junctions, 50%, three junctions, 56%, and so on. By the way, 50% would be an incredible number, right? Think about it this way. half the energy of light that falls on the solar panel, if it gets converted to electricity, that will be immense. I mean, that's a huge, huge. No one's close. The world record today is about 43%. We're getting close, but it's not quite there yet. And that's a very complex system. We'll talk more about that later. This is also assuming 1,000x concentration. So 1,000 suns here means you have a parabolic concentrator or a CPC or something that is concentrating by a factor of 1,000. So which we all know is difficult to do, but it's doable, right? Anyway, so that's the way to get a very high efficiency. And this is important primarily for space applications. So the Mars rover, for instance, has something like this, right? Because you need a lot. I mean, again, if you think of the Mars rover, it's only like about the size of this table, 6 feet, something like that. And then, you can maybe deploy a little bit more in terms of solar panels to collect energy, but not a huge amount of area. So you want to get as much efficiency as possible, and it's heavy, right? And it's expensive to send these very heavy things to space. Okay. We'll talk more about this when we talk about the spectrum splitting, which is another way to achieve it. So I'm going to skip that part for later. So, so this is another way to look at what I just said. Here we're showing 3 cells, gallium indium phosphide, shown in blue, and this is plotting quantum efficiency, as we know, which is how efficiently is a particular photon absorbed as a function of the wave in the horizontal axis. So gallium indium phosphide absorbs quite nicely in the blue wavelength. So now it's wavelength, not energy. Okay, the energy is increasing right to left. Gallium indium phosphide absorbs the blue color, gallium arsenide absorbs green, and the germanium absorbs the redder stuff. By putting them all together, you can get all of them very efficiently. Same idea, but you can do it with 3, 4. The world record is 4. I think people have tried 5. It's really, really tough to do, which we'll talk about the reasons why. The reason why, actually, it's like here, is because taking different materials, if you take simply 2 different materials and stack them on top of each other, that doesn't work so good. Why? Because there is an air gap between them. So you have this material, air, then the next material, and so on. The light will bounce off the air. So you'll get huge reflection losses. Things will bounce around and so on. So you will not absorb the light so efficiently. You'll lose huge amounts of losses. To avoid this, people come up with very complex structures. An example is shown here with three devices. So how do you understand this image? So first of all, let's start with the bottom. So you have a silicon or a glass handle, which is basically a substrate which is used to carry things around. So it has no electronic function. Okay, it's just a handling wafer. Let's ignore this stuff. There's just a little bit of material here to support the rest of it. This red part here refers to the bottom junction with a low band gap, which is 1 eV. So it will absorb all the red photons, the right-hand side we saw. And in this example, they're using gallium indium phosphide in some particular alloy. But it's not a simple thing because you have to kind of control it very precisely, alloy with some other things, because it is grown 1 atom at a time, atomic layer at a time. You put down the atoms of this to build this up very precisely. It's very complex, very slow, requires very high vacuum, lots of energy and so on. That's why this turns out to be a very expensive solar cell. And then you have the next cell up here, which you can see, 1.4 EV middle junction. So this is 1 EV, that's 1.4 EV, so it's higher. But then there is this whole transition layer, which is very complex. And the reason for this is 2. 1, you want that transition layer to be very transparent to the red photons, so they'll pass through. You don't want it to be absorbed, right? Second, you also want it to be a good conductor of electricity. Why? Because the electrons that are generated here, they have to pass through here, all of these, all the way to the contacts. So they need to be a very good optically transparent, but also a very good electrical conductor. Turns out to be a difficult problem. The other reason why you need a transition region here is because the lattice structure of this material may not match the lattice structure of this material. So two different crystal lattices, you cannot grow one on top of each other. There will be too many defects. Defects are bad because that's where the electron and holes get trapped. And that's the efficiency loss for the system. So these are very important technological reasons why this has been done with what's called epitaxial growth, where you draw one layer of atoms at a time. Very complicated system. In fact, I should have mentioned Nakamura, who gave the Judd lecture, some of you might remember, at the College of Engineering, last fall or spring? Fall, yeah. But a year ago, I guess, during COVID, if you did watch it, he won the Nobel Prize for using these kinds of technologies to develop the blue LED, which is basically grown in a very similar fashion. By the way, as I said at the very beginning, a good LED is also a good solar cell. A good absorber of light has to be a very good emitter of light. This comes from thermodynamics. And this development of such a process, so it's really an engineering feat that won him the Nobel Prize. So it was a very important advancement, of course, but it's related to that. He's a material scientist. Anyway, yeah, so and then you have the top cell. There's a smaller transition layer here. The top cell, of course, has the highest band gap, 1.8 eV in this case. And again, in this example, the materials are all indium, gallium, and arsenic with some sort of zinc base. They're different alloys, and you're using the different alloy compositions to adjust the band gap. There's one way to do it, not the only way. It's very complex, lots of different ways people do it. So the problem with this, as you can imagine, there are two problems. One is, as I said, the manufacturing process is very complicated. You have to do it very slowly, one at a time, very low defect, and so on. The second problem is that these materials tend to be very expensive. Gallium arsenide is about, per gram, is about 10,000 times more expensive than silicon. So you can imagine, you also don't want to use too much of this. So in the old days, people used to simply use a gallium arsenide wafer to grow all this stuff. But more recently, people have come up with these approaches to use much cheaper silicon or glass wafers and simply use that sacrificial layer to peel it off and then reuse the material and so on. And that's the premise of this company called Alta Devices, which I think there's a video, if I remember right. But those are the main things I want to talk about. So just make sure I don't forget, this is a triple junction cell, there are 3 junctions. It's made on a germanium substrate. Germanium is also a very expensive material. Spectrolab is a company which I think was purchased by Boeing, which showed the world record efficiency at that time. Yeah, those are the main things. Yeah, I think I skipped the video, but I should just mention there's a startup company. It's not that small anymore. Spun out of Caltech, which developed a technology which is shown here, where they, instead of using an expensive germanium substrate, they use silicon or glass, and simply you're able to peel it off and keep reusing it. So you can make these cells in a more cost-effective manner. Okay. Then the last topic I want to talk about before we end this part is to understand, is quantum efficiency greater than 1 possible? Right? Now, let's understand, what does quantum efficiency mean? Quantum efficiency means is the number of electron-hole pairs that are created for every photon that's absorbed. In other words, if I have a photon going in, getting absorbed in the solar cell, and I get 1 electron-hole pair in the best case, that's 100% quantum efficiency. The question is, okay, can I get more than 100%? Of course, if we just ask that question, it's a little bit absurd, right? I only have 1 photon. Why would I get more than 1 electron-hole pair? I only 1 event. Turns out that's actually a little bit naive. It's actually not true. You can get more under very special circumstances. So I just want to point that out because it's very interesting, and it hopefully will connect with some of your intuition. So the answer, of course, is yes. Otherwise, we won't be talking about it. In a very important paper, a little more 10 years ago, this was actually shown. And the idea is that if you have, let's just go through here first, 1 photon with sufficiently high energy, okay, so blue or UV or something like that, can generate 2 or more electron hole pairs. So instead of just creating 1 electron hole pair, you have enough energy to create more than 1. And we'll see how that is. This phenomenon is called multiple exciton generation, or MEG. It has been known for several decades in photovoltaics as a very small effect, but not very efficient. It can be done with much better material science, which is what they did in this particular case. They were able to collect these carriers more efficiently to show that you could increase the current. Now, of course, greater electron hole pairs means you're getting more current. That's really what you're looking for, the same voltage, right? Since current times voltage is power, that means you're getting more power, obviously. So this is just showing, okay, this is the internal quantum efficiency versus the energy of the photon. This is, the energy of the photon relative to the band gap, h nu over Eg. Eg is the band gap of the material. So here you can see the numbers are going above 100% in this particular situation. And they did it for 3 different band gap materials. In this case, it's a quantum dot, but you don't need to worry about exactly why that matters. So how does this work? Like, why does this happen? There are 3 approaches to this, and that's useful to understand because it's very intuitive. And once you understand, it's kind of common sense. MEG refers to multi-exciton generation. So you can have a down conversion, which is basically you get these high energy blue photons, gets down converted to lower energy red photons. But remember, I asked you a couple of months ago, if you had a blue laser and a red laser, or in that case, I asked the green, but let's say a blue laser and red laser of the same power, which has more flux. Obviously, the laser of color, lower energy, has more flux because every photon has lower energy. That's the situation here. Here, this has more energy, but lower flux, smaller number of particles. Once I can convert it to lower energy photons, I have higher flux. Now, flux is directly related to the electron hole pairs, right? Because 1 photon gives 1 electron hole pairs in the normal case. So that's exactly what's happening. I have blue photons come in here. Each blue photon gave me 2 red photons. So 1 blue photon gave me 2 red photons. Each of these red photons gives me 1 electron hole pair. So now I have 2 electron hole pairs per blue photon. How does that work from an energy band diagram, very simplified band diagram? You have the blue photon with lots of energy coming in here. The electron gets excited from the valence band all the way into the conduction band, but way into the conduction band, not close to the band edge. It relaxes very quickly. That's a very, very quick thermodynamic process. Now, instead of relaxing directly and fluorescing or emitting light, it goes through 2 steps. It relaxes to an intermediate level. So the material is engineered to have this intermediate level, emitting a red photon, and then it relaxes again, emitting another red photon. So you end up having 2 photons here. And that matches the band gap of the silicon in this example, Eg of silicon. So 1 blue photon now gave me 2 red photons and 2 electron hole pairs, essentially getting me external quantum efficiency larger than 1. The other way you can do it is something called downshifting, where, say, in this case, blue photons come in. I get the same number of red photons, but I have energy absorption such that I get an extra electron hole pair, which is shown here. So let's look at it energetically. Blue photon comes in. Again, the electron is excited way above the conduction band, relaxes rapidly, and then it emits a red photon. But a red photon now excites the electron hole pair much higher than the band gap of the silicon. And this extra energy can then be used to excite another electron hole pair rather than just being relaxing to the band edge. That's actually not very common and not very efficient to actually do. The more common approach is what's shown here, which utilizes an up converter, also difficult to do. But in this case, the blue photons pass straight through the solar cell, and there's an up conversion. Some of them, not all of them, some of them are absorbed, of course. The up conversion simply converts it to lower energy photons with more flux, the more number of photons. Again, energy band diagram is easier to understand. You come in with 2 red photons, you get these 2 absorption events, and generating 1 yellow photon, so it has higher energy than which is then absorbed by the silicon. So anyway, this one's a little bit confusing because what's happening is that the blue photons pass through, and you're simply reflecting with this upconverter with this yellow photon, which is then absorbed by the source. So you get this extra effect as well. But nevertheless, just be aware that there are different ways of increasing the quantum efficiency. It's still under research. Lastly, there exists various interesting types of solar cells. As an example of a radial Pn junction solar cell. So instead of having Pn junctions which are stacked on top of each other, which is typically the case, you can have radial junctions. And the reason for the radial junction, and there are 2 reasons. One is that this increases the surface area where the light can get absorbed, and it reduces the distance that the electron hole pairs have to travel to reach the electrodes, because now the junction is really small, right? It's just this really little microscopic or nanoscopic wire. So there are different ways this can be done. So there's some advantages as well. So in summary, photovoltaics, of course, has grown exponentially over several decades now. We talked about Swanson's law, similar to the Moore's law in transistors. Most importantly, just if you remember, this is what you remember, solar cells require absorption of the light, separation of the electron hole pairs, and then collection of these electron hole pairs in the electrodes to drive the current through a load. So silicon is obviously the most popular thing, but there are other materials as well. Certainly the 3rd generation and so on. And we'll come back to this point when we talk about spectrum splitting. Oops. Okay, let me. I don't know why I changed my. Let me fix my display. Okay.